Hello, I will talk about special relativity. There are three phenomena that occurs when someone is traveling at very high speed close to the speed of light. The first phenomenon is the increase in mass. The second phenomenon is length contraction, and the third phenomenon is time dilation. I will start with the increase in mass. Suppose the twin brother who goes on a journey in space weighs 98 kilograms. So, first of all, we will calculate what his mass is. What is the mass of the twin brother that weighs 98 kilogram on Earth? So the question is weight equals to the mass times g. G is the gravity on Earth. That equals to 9.8 meters divided by second squared. So that means that if you throw something from a building, if you throw something from the roof of the building to the ground, so the velocity of the object will increase every second by 9.8 meters per second. Yes, so in the first second is the velocity of the object that you threw from the roof of the building will be 9.8 meters per second, and then it will be in the second it will be about 20 meters per second, and in the 10th second actually it will be about 98 meters per second. So in the 10th second actually the object will pass 98 meters, because every second its velocity increases by 9.8 second per meter. Yes, so if you want to simplify it, you can say that every second the velocity of the object increases in about 10 meters per second. So in the first second the velocity of the object will be 10 meters per second. In the second it will be 20 meters per second. In the third second it will be 30 meters per second, and so on. And in the 10th second it will be about 100 meters per second, because in every second the velocity of the object increases by 10 meters per second. Actually, that is the definition of acceleration. Yes, so the weight of the twin brother is 98 kilograms, and the weight equals to the mass times g is the gravity, that is, as I have already said, 9.8 meters divided by second square. So 98 kilograms equals to the mass times 98, that is the gravity on Earth, 98 meters per second square. So the mass of the twin brother that weighs on Earth 98 kilograms will be 10 kilograms. Okay. So on Earth the mass of the twin brother is 10 kilograms, and when it will move in the spaceship and at the speed of 80% of the speed of light, that is 240,000 kilometers per second, according to the mass increase equation of special relativity, his mass in space will be about 16.33 kilograms. But he will not feel it, and if his twin brother has a mass detector, the detector will measure 16.33 kilograms. That means that his mass is increased by 63.3%. Okay, so now I will explain the equation of the mass increase. M equals to the mass of the object or the twin brother that flies on the space or in the spacecraft at very high speed, and m naught is actually the rest mass, or his mass at Earth when he is not moving, that is 10 kilograms, as we already calculated, and we divided it by the root of 1 minus v squared divided by c squared. So his mass in the space when it travels at the velocity of 80% of the speed of light, that is 240,000 kilometers per second, his mass will be 16.33 kilograms. So actually his mass increased by 63.3%. Okay, so m is the mass of the object or the twin brother when it travels in space at very high speed, close to the speed of light, and m naught is the mass of the object or the twin brother on Earth when you weigh him when he is not moving, or when the object is not moving. Okay, so now I will talk about the second phenomenon that occurs when someone is traveling at very high speed in space, and the phenomenon is length contraction or shortening of distance. When you measure a distance between two objects that are not in motion relative to each other, let's assume that you measured a certain distance. So the distance between them will shrink when one of them moves at a very high speed, close to the speed of light relative to the other. So when you measure the distance between two objects when they are not moving relative to each other, if you measured a distance, that distance will shrink when one of the objects is moving at very high speed towards the other object. Okay? For example, as mentioned, the distance from Earth to the star Epsilon is 10 light years when you measure it from Earth, but when you measure the distance from the spaceship that moves in space at a speed of 240,000 kilometers per second, then the distance will be shrinked to 6 light years only. And that is from the point of view of the twin brother flying in the spaceship. So in our example, actually the distance from Earth to the star Epsilon is 10 light years, and that distance is measured when the two objects are not moving relative to each other. The Earth is not moving relative, or our Sun, yes, is not moving relative to the star Epsilon, because actually the distance between them is constant. All the stars actually are moving around the center of the galaxy, but relative to each other they are not moving, because for example, if this is our Sun and this is the star Epsilon, both of them moving around the center of the galaxy, and they are making one round in about I think 2 million years. So, but relative to each other, they are not moving. They have constant distance relative to each other. So, when you measure the distance between star Epsilon and our Sun, or the Earth, the distance is 10 light years. But when the twin brother is moving in the space at very high speed towards the star Epsilon, then the distance between Earth and the star epsilon will be shrink to 6 light years only. So L is the distance between two objects on space when one of the objects is moving towards the other object in very high speed. And L is the distance between the two objects when they are not moving relative to each other. And we multiply it by the root of 1 minus v squared divided by c squared. So, in our example, the twin brother moves at a speed of 240,000 kilometers per second towards the star epsilon. So we divided his velocity, the velocity of the twin brother squared, by the speed of light squared. And we get the result of 6 light years. So the distance between the two objects, that is to say the Earth and the star epsilon, shrinks from 10 light years to 6 light years only. So that phenomenon is called the contraction of distance. Okay? Because according to the special relativity, when you measure the distance between two objects, you will get the result, but that result that you get will be shrinked if one of the objects is moving towards the other object. Okay, so in our example, the distance from Earth to the star epsilon shrinked from 10 light years to 6 light years only. Okay, but in addition to that, the height of the man in the spaceship also shrinks, and if on Earth his height is 1.8 meters, then from the point of view of the twin brother who remains on Earth, the height of the twin brother in the spacecraft shrinks to only 1.08 meters. And if the twin brother that stays on Earth had a height detector, then the detector would show a height of only 1.08 meters. But the twin brother who is in the spacecraft doesn't feel that he is shorter. So I will explain the equation. L is the height of the twin brother that is traveling in the space toward the star epsilon at the speed of 240,000 kilometers per second. And actually, in our example, is 1.08 meters, and L naught is the height of the twin brother on Earth. That in our example is 1.8 meters. And we multiply it by the root of 1 minus v squared divided by c squared. So in our example, as I've already said, L naught is the height of the twin brother on Earth when he is not moving. We multiply it by the root of 1 minus the speed of the twin brother that is traveling in the spaceship towards the star epsilon at the speed of 240,000 kilometers per second, and we square the velocity, and then we divided it by the speed of light squared. And the final result is 1.08 meters. So we see that his height, the twin brother's height, is actually shrinked from 1.8 meters to 1.08 meters only. So it actually shrinked by 72 centimeters. Okay. Now I will talk about the third phenomenon that occurs when someone is traveling in space at very high speed. And the phenomenon is time dilation. As mentioned, from the point of view of the brother who is on Earth, his twin brother is moving in the spaceship at very high speed. Therefore, the rate of time flow in the spaceship will be slower than the rate of time flow on Earth. While on Earth it took him 25 years for the twin brother to return from a journey in space, in the spaceship the total time that it passed is 15 years only. So, first of all, I will explain the equation. T is the time that is passed in the spaceship, the time that is passed for the one that is moving at very high speed in the space. And T naught is the time that is passed on Earth during the journey. And we multiply it by the root of 1 minus the velocity of the one that is moving in the space at very high speed, and we square it, and then we divided it by the speed of the light squared. So in our example, the total time that is passed on Earth, that is T naught, is 25 years. And we multiply it by the root of 1 minus the velocity of the twin brother that travels in the spacecraft towards the star epsilon, that is 240,000 kilometers per second. And when we square it, and then when we divided it by the speed of light squared, the result is 0.8 squared. And 1 minus 0.8 squared is 0.36, and the root of 0.36 is actually 0.6, and 0.6 times 25 equals to 15 years. So the total time that is passed in the spaceship for the twin brother that travels in the spaceship at the speed of 240,000 kilometers per second, the total time is 15 years only. So you will return to Earth. When you will return to Earth, you will be 10 years younger than his twin brother that stayed on Earth. And that is because of the fact that the time flow in the spaceship is slower than the time flow on Earth, or the rate of time flow in the spaceship that travels at very high speed is slower than the rate of time flow on Earth. That is the reason that the total time that is passed in the spaceship is less than the time that is passed on Earth, okay? And that is from the point of view of the brother that stays on Earth. While from the point of view of the twin brother who embarked on a space journey towards the Epsilon star, he is at rest, and the Epsilon star is moving towards him at a speed of 240,000 kilometers per second. Therefore, in this situation, there will be a contraction of distance according to special relativity. And the total distance between the Earth and the star Epsilon will be 6 light years only, and the round trip distance is 12 light years, and at a speed of 80% of the speed of light, the entire journey in a spacecraft will take 15 years due to the contraction of distance. As I have already said in the previous lecture, from the point of view of the brother that is traveling in space at very high speed, he is at rest and the star Epsilon is moving towards him at very high speed. And in this situation there will be a contraction of distance, or the distance between him and the star Epsilon will be contracted from 10 light years to 6 light years only. So the total distance that he must travel back and forth is actually 2 times the distance between him and the star Epsilon, that is 6 light years. 2 times 6 light years is 12 light years, and he does it at the speed of 80% of the speed of light. So the total way that he must do divided by the speed is the total time that is passed for all the journey from the point of view of the brother that is traveling in space towards the star Epsilon. So the total time that is passed is also the same result as the previous analyzation of from the point of view of the brother that on Earth. The total time that is passed is 15 years only. Okay, thank you very much.